Circle of doom. Yes, you may start now.
I'll start? Okay, thanks. Yeah, thanks, Suresh, for letting me speak to the students, MSc students. So we haven't yet had the pleasure of having you here. And I can't see you, unfortunately, in this setup that I have with me right now. So how many of you are out there in the class, roughly?
50. At this point,
50. Okay. Yeah, actually, this time we had, I remember that we had 54 of them join on the pure MSc batch.
Last time 60 plus.
Yeah, because we have our dual degree students as well. So it's fantastic, and hopefully we will see you soon. So today, Suresh has asked me to talk about integrability and non-integrability, which is really a very big subject. I'm going to talk about a small part of it and what I can talk about. It kind of extends into areas of statistical mechanics, quantum mechanics, and so on. And it's an old subject which is still of very much great interest, contemporary research interest. So I wish to give you some idea of it, and it follows naturally within classical mechanics. Since I cannot see you, I would very much appreciate if you stop me at any point, and ask me questions if there's something which is unclear. So at the center of the issue of whether some system is integrable or not integrable is the issue of whether there are constants of motion or not. Okay, so first of all, we assume that we have some Hamiltonian system, okay, and described by a Hamiltonian. So that is this H, which I have written here. There are some number of degrees of freedom, and I'm calling it small n in my presentation here. Small n is the number of degrees of freedom, and therefore the dimensionality of the phase space is twice that, because you have the number of degrees of freedom, then the corresponding coordinates, generalized coordinates, and their corresponding momenta. So they form a 2n dimensional space, even dimensional, and the classical mechanics is a flow in this phase space. So that's what we have. But along this trajectory of any flow, you start some initial condition and you flow along from that initial condition along with time. You flow to a different state at a later time. That's what the study of these states is classical mechanics. Now, that equation of motion is Hamilton's equations that describes to you the flow. And what is a constant of motion? Constant of motion is something which you calculate at some phase space point, and I'm just denoting Q and P. This Q itself can have n components to it, P can have n components to it. I'm just writing it as QP rather than Q1 to Qn, Pn to P1 to Pn. This itself is a constant of motion if it is not changing with time. That's what a constant means. Okay, so it's a non-trivial constant is some function of the phase space variable which is not changing with time, although the coordinates and the momenta are themselves changing with time. Okay, so that is, but still there is some peculiar functions of these positions and momenta which are not changing in time. If that is the case, then you call it a constant of motion. And again, I'll ask you some questions because I'm coming in the middle. Poisson bracket has been introduced.
Yeah, we have gone up to Hamilton-Jacobi.
Okay, so
you have all these things like this first slide. They know.
They know. Very good. So so then you know that if you take a derivative of this function, you will have a derivative, partial derivative f with respect to q, and then dq by dt, and for which you can substitute Hamilton's equations, derivative h with respect to p, and similarly for dp by dt, and then you will get this thing. And in fact, this is the central sort of, one of the important meanings or interpretation of the Poisson bracket itself, that the derivative of this function is nothing but the Poisson bracket. And therefore, if this has to be constant, and you see this is the total derivative, so this total derivative means that you're flowing along with you're going along with the flow, and therefore, for this to be constant, a necessary and sufficient condition is that its Poisson bracket vanishes. You see, I'm assuming that f is independent of time itself, explicitly independent of time. Therefore, if its Poisson bracket vanishes, that's a constant. And clearly, h itself is a constant, and that usually has the interpretation of energy. Now, if f1 and f2 are two constants of motion, we can actually get a third constant of motion by just taking its Poisson bracket. So this seems to be a nice way of getting constants of motion. And you can prove this by the Jacobi identity satisfied by the Poisson brackets. So if you are given two constants, you can get another constant. This seems to be a good trick because you can go on constructing constants of motion. But probably know that this is not the case. We cannot have very many constants of motion. What is the maximum number of constants of motion we can have? If you have n degrees of freedom, as I said, the phase space is 2n dimensional, and the flow is a 2n dimensional, is a flow in this 2n dimensional space. If you have two, this is an independent statement independent of that. Suppose we have two functions, f1 and f2, that are constant. So the c1 and c2 are constant. So f1 is c1, f2 is c2. These are describing, each one of them is describing a 2n minus 1 dimensional surface, or a higher dimensional surface. Because of this constraint, this minus 1 is there, this constant is there. So it's constraining the 2n variables by 1, and therefore it's a 2n minus 1 dimensional surface. But if both of them are constant, then the orbit has to lie at an intersection of these two surfaces. And therefore, the intersection of these two surfaces decreases by 1 more, and therefore is a 2n minus 2 dimensional surface. So you see, with each additional constant, so if you have just one constant, there is a 2n minus 1 dimensional surface on which we can expect the orbit to roam around. If there are two, it decreases by 1 more, 2n minus 2. And so if you have more and more constants of motion, you will have the surface on which the orbit is constrained to lie keeps decreasing. How much can it decrease? After all, a phase space has to have some dimension. The orbit itself, recall, is just 1 point. It's just a trace of 1 point as time goes by. So it's a one-dimensional curve. It's a one-dimensional curve in a 2n dimensional phase space. That's what a phase space orbit is. And therefore, there cannot be any more than 2n minus 1 constants of motion. Because if you have 2n minus 1 constants that are these surfaces, and their intersections defines a one-dimensional orbit. So you cannot have anything more than 2n minus 1 constants of motion. That's a maximum number of constants of motion. For example, we look at some simple examples. So 1 degree of freedom, n equals 1. N equals 1. Energy itself is a constant because we are assuming a Hamiltonian system in which the Hamiltonian is explicitly independent of time. Then the energy is a constant, so H equals E is typically energy, is a constant. And the maximum number is 2 into 1 minus 1, which is 1. So that's it, it's finished. So 1 degree of freedom, the maximum number of constants of motion is 1, and therefore you cannot have any other constant of motion apart from the Hamiltonian itself. In a 1 degree of freedom system, you cannot have any further constants of motion than the Hamiltonian. 2 degrees of freedom, n equals 2, then energy is still a constant. What is the maximum number? 2 into 2 minus 1, which is 3. So there can be an additional 2 more constants of motion apart from energy. But actually, generally, why should there be these constants? So this is the meaning of the word generic. Generic means generally in a more scholarly way. So generically, none of them exist. I mean, no other constant of motion apart from energy exists. And the motion happens only on this 3-dimensional energy shell, H equals E, for a given energy E. For a given energy E, which is determined by the initial condition, typically an orbit just roams around this 3-dimensional surface. But there are special conditions, in fact you would have studied these examples already, where there are more constants. So one of the most important things which you have already studied is the case of central forces, where the potential energy depends only on the distance from some point. We'll say that that's the origin. So here this v of xy and is only a function of the polar coordinate. There's only n equals 2, this polar coordinate and its angle theta. Okay, so it's only a function of this rho. It's not a function of theta as it can be in general. And here there is an LZ. Therefore, now you have this Lagrangian equations. So the Lagrangian equation will be independent of theta. Okay, you know that there is a theta dependence, a theta dot dependence, and a rho dot dependence. So you apply, this is the Lagrangian of this central force potential. So you see that d by dt of this derivative is equal to derivative of the Lagrangian with respect to theta. But since that is 0, so this itself, the derivative is equal to 0, and therefore this quantity is a constant, which you know is as the interpretation of angular momentum. So angular momentum is a constant, which is just coming from the fact that there is a symmetry of rotations, and therefore this quantity, this combination, rho squared theta dot, is a constant. Although theta is changing, rho is changing. Okay, but this LZ, angular momentum, is a constant. So now we have two constants of motion. It can still accommodate one more constant of motion, a central force potential, but in general that does not exist. In general, there is no one more constant. That means that even I said that actually generally there is none except energy. But if you say, well, there is the symmetry of being invariant under rotation, then generally there exist two constants of motion. But if you give me some even more specific potentials, central potentials, like 1 over rho, which should be like a two-dimensional version of the Kepler problem, or a harmonic oscillator version. So kappa rho square, so that is just x square plus y square. So it's a two-dimensional harmonic oscillator. Then there exists an additional constant of motion. Okay, there exists an additional constant of motion. You can construct them. I'm leaving that, probably you already know what it is, but it is very interesting to construct these additional constants. And therefore the total number of constants is actually 3. Maybe in this simple case I can actually ask for some feedback. What do you think will be this third constant of motion in the case of a harmonic oscillator like this, kappa rho square? Okay, so I want you to think of it as just an uncoupled two harmonic oscillators. So x square plus y square is the potential energy. Okay, so angular momentum is a constant, energy is a constant. What is this third constant? Can I have some guesses from any of you?
So can you say frequency is constant?
Frequency is a parameter. Okay, you're saying something like this k or something, right? Something related to k. But those are just parameters. Mass is a constant, of course, but we don't consider these things as constants. So this is very essential. That's why I said a non-trivial constant is a function of phase space variables. Try again.
So the Poisson bracket of energy and angular momentum.
Sorry, say that again. I can't hear you clearly.
The Poisson bracket of energy and LZ, we calculate that.
So you're going back to my first slide. You're taking two Poisson brackets. Poisson bracket of, well, do it and see, but without doing that exercise, and maybe you won't get
zero. But that is zero. That is zero because LZ with H is LZ is a
the H. Yeah. Sorry, yes. That is zero. Yeah. You see, if one of these things itself is energy, which is what I think you suggested, then as Suresh is saying, that's just zero, and zero is a trivial constant. We won't consider that. Tell me something else.
The area velocity.
aerial velocity. What is aerial velocity?
I mean, the area it covers for a certain time.
Area of what? We are talking about some general thing. Huh? I mean, so you have in mind already some ellipse and all that kind of things. I think we're not talking about very general. We're talking about just about uncoupled harmonic oscillators. So the potential energy is just some constant times x square plus y square. In fact, what you would call it's called isotropic harmonic oscillator, because the frequency is the same in both the x and y direction. Try again. So you see, the key word here is uncoupled harmonic oscillators. Okay, the key word is uncoupled. That's the clue. Try again. You know it.
Sir, is angular momentum being conserved in another direction also?
There is no other direction. There is only one LZ. This is just a two-dimensional harmonic oscillator. So there is one direction outside. There is other directions, it will vanish.
Are there separate Hamiltonians conserved?
Exactly. Very good. So the separate, by that you mean x and y. Okay, so the energies of x and y, because it's uncoupled. You see, there is no interaction between the two harmonic oscillators. So when you look at it in polar coordinates, it looks coupled. Okay, you'll have some rho dot square, rho square, theta dot square, plus rho square. Okay, so it looks kind of more. But when you look at it in the, well, theta doesn't even appear there. But if you look at it in the x and y, it's just uncoupled harmonic oscillators. So the energy of the individual ones will be a constant. So not only the total energy, which is of course a constant, but also the individual energies. But you can't have both of them to be a constant, because the sum of that is, both of them are constants, but they are not independent. If you take the total energy, then that's simply the sum of the individual energy. So the three constants in this case of this harmonic oscillator are angular momentum, total energy, and energy of any one of the oscillators. So px square plus x square, let's say. Okay? So constants of motion, in this case, we can identify them easily, but typically they cannot be identified easily. And not only can we not identify them easily, if you do identify them, it's not obvious that they are coming from some continuous symmetries. Okay, so in this case, where it's coming from a symmetry of theta. So I'm just warning you in general. In fact, it's an open problem even today, that if you are given a Hamiltonian H, just classical problem, in some number of degrees of freedom, find out is there an algorithm which will find out all the constants of motion? Answer is no, surprisingly. Okay, so let's move on. Are there any questions at this point?
So,
Yeah.
so you said that energy of any one of them is constant. So why not the other one? Like energy of one of them is constant and the total energy is constant. So the other
Energy of
one.
the other one is also a constant. So let's call it E1, E2, and total as E. Okay? E1 is constant, E2 is constant, E is constant, but since E1 plus E2 is E, they are not independent. All three are not independent. You can choose any two of them. Say E1, E2 and angular momentum, or E1, E and angular momentum, or E2, E and angular momentum. But if you take, there can be only, if you have four constants, you can be sure that they are not independent. That means there is some function of them which vanishes. In this case, E1 plus E2 minus E. Is that clear?
Yes.
The other, yeah, okay. Any other? So there is a definition of integrability. Now we come to integrability definition, a formal definition of integrability, and this is associated with these names. Liouville you would have already heard of. You would have studied the Liouville theorem and so on. If you're not, you will study. A very famous person, and Arnold is also very famous, but you may not have yet heard of him. Vladimir Arnold, from the last century, mathematician, physicist. So this is, he formulated precisely several important classical mechanical theorems apart from several theorems in mechanics. He has a very famous book called Mathematical Methods of Classical Mechanics for those who are so inclined, which is really if you want to really learn classical mechanics, you have to understand Vladimir Arnold in some sense. Okay. So what is this definition? Let's just go through it. F1 to Fk are said to be in mutual involution. If their pairwise Poisson bracket vanishes. For every pair of this K and L, their Poisson bracket vanishes. Then you say that this set is in mutual involution. Okay, just a word, but that's a definition. And this is a fact which you can prove. If there are n degrees of freedom, then there can be at most n functions in mutual involution. Okay, it's not hard. You try to prove it. I'm not proving it here. How many functions can you have at most that are in mutual involution? There can be only small n number of, where n is the number of degrees of freedom. You see, it's not 2n minus 1, or we said that there can be 2n minus 1 constants of motion. But if you ask how many of them are in mutual involution, the maximum is only n, which is the number of degrees of freedom. If you have n plus 1, then it means that they are not independent, just as we had this E1 plus E2 minus E equal to 0. So they are not independent. Okay. Hamiltonian H is said to be integrable if there exists n independent constants of motion that are in mutual involution. You see, there is a surprising fact here. We have so far said that there can be a maximum of 2n minus 1 independent constants of motion. Now we are saying that actually it is sufficient to have only n independent constants of motion, and that is sufficient for the system to be so-called integrable. But there is this additional condition that they be in mutual involution as defined by this. Okay?
Arul, shouldn't it be the system which is integrable?
Yeah. Well, this is also loosely said. A Hamiltonian H is sort of describing the system.
Okay, Hamiltonian system. Okay.
Yeah.
Sir,
Okay.
what do you mean by mutual involution? It means the Poisson bracket is 0?
Yes, that's what it means. Are you asking what does it imply and so on with respect to further things?
I will discuss this condition, what this condition implies next lecture.
Yeah,
So,
very good. Okay, thanks. So let us just go with this definition. Okay, the definition is clear. That there has to be sufficient. You see, so if typically one of these things will be the Hamiltonian itself, and of course every other things will then be constants of motion. A Hamiltonian itself will be a constant of motion. You will have n constants of motion. So that is what this n independent constants of motion that are in mutual involution. All 1 degree of freedom systems are integrable. That is clear because there is just one H which is needed, and there can be just one of them. So that's independent. So integrable systems, all 1 degree of freedom. It doesn't matter whatever the potential energy may be, x power 4, sin x, cos x, whatever it may be. Okay. Integrable systems are in some sense solvable. That is why it's important to this thing. In some sense, they are solvable. Their motion can be reduced to quadratures. Quadratures mean some kind of integral. Okay, and how that works is actually through this thing called action angle variables, which you might have already come across. So if H is
again, this is something I am not done. We'll be doing tomorrow.
Yeah.
But doesn't matter.
Doesn't actually motivate action angle variables, which will otherwise seem rather mysterious. So if H is integrable, then there exists a canonical transformation from these generalized coordinates and momenta to action angle variables, which are again some kind of momentum and coordinates. So, but these coordinates are angles, theta I, such that the Hamiltonian is only a function of these actions. Okay, there are these n actions. Okay, so this is what it says. If it is integrable, then there exists a canonical transformation. Canonical transformation is already discussed. Suresh?
Yes. Yeah. We're done with all this.
Yeah. So this canonical transformation, you understand. So these are also canonically conjugate variables, but such that the new Hamiltonian is very simple. It doesn't have any of the thetas in it. You see, that is sufficient because of the because if you look at the Hamiltonian equations of motion, because there is no theta there, I dot. What is the value of I dot? For any of these action, let's take I1. What is dI1 by dt? Anyone? Suppose your Hamiltonian is only this. What is dI1 by dt? Hamilton's equations of motion. Partial derivative with respect to what?
So it will be 0.
Theta.
Theta 1 to be precise, right? But theta 1 doesn't exist here, and therefore it's 0, and therefore I1 dot is 0. So all these things are constants. That is what actually makes this, that's why it's sufficient to have n degrees of n constants, because you have these other theta 1 dot. Okay, so all these are constants, and therefore theta 1 dot. What about theta 1 dot? Theta 1 dot, is it a constant or not? From Hamilton's equations of motion again, theta 1
So
dot is
won't that be equal to dou h by
dou h by
it will be dou h by dou I1, right?
dou I1 with a negative sign and so on. Is that a constant?
Yeah, that's
It is a constant because it itself is a function of, it's a function of all these actions. But the actions are themselves constant, and therefore theta 1 dot is constant. So actually then you can immediately solve the problem. You're done. Because theta 1 dot is constant is the simplest differential equation, even I can solve it. And it's theta 1 equals this constant, let's call it omega 1. Omega 1 into t plus theta 1 dot, or I'm sorry, theta 1 at time 0. So we can solve all the Hamilton's equations of motion immediately once this is there. Therefore, it is in some sense solvable. So the integrable systems are solvable because we can solve it in this I theta in a trivial way, and it's just a canonical transformation away. So we can just do the transformation and find Q and P. Okay, so you will do some examples, elementary examples and so on. Okay. But this is a very general statement that if it's a very non-trivial and general statement, that if there are these constants of motion that are in involution, as I defined in the previous slide, then there exists a canonical transformation from these to these action angle variables such that the Hamiltonian is only a function of these. And now how are these actions constructed? These actions are in general functions of these involutions, these constants. They are not themselves directly given by these f's, which themselves could be constants, but they are in general not. They would be some functions of these functions fi. Okay. And how do the phase space trajectories look? Phase space trajectories are now confined to surfaces that are topologically n-tori. That is, an n-torus is a Cartesian product of n circles. And where are these circles parameterized by? Well, they're just parameterized by these angles, because these theta 1 to theta n, they are the ones which are parameterizing these things. Okay, and these so those are the coordinates on this torus, where this is a circle, etc., are coordinates on them. So here is an example of a two torus, which is just got two circles, so topologically two circles together. This is something which we can immediately visualize as some object like a vada. Okay, so here you have these one circle direction and the other circle direction. So the motion on this is of a 2 degree of freedom system, which is integrable, is in general topologically on these kind of tori. Okay, so that's an integrable system according to Liouville and Arul. And you know already that there are some, we have discussed examples like this, where there are these things are integrable. So here are, and if the number of independent constants is larger than this n, then the systems are said to be super integrable. Okay, so that sounds good. So we have integrable systems, and if the number of constants is in excess of the number of degrees of freedom, it's super integrable. We have already come across a super integrable example, namely
Sir,
harmonic oscillator.
is it because I1 is constant, or like for 2 n is equal to 2, is it because I1 I2 is constant and we are having two angles theta 1 and theta 2, that it is like two perpendicular circles which make the torus? Why
Not
is it
necessarily
specifically
perpendicular
torus?
or something, but okay, in a 2 degree of freedom, integrable. Okay, it's not guaranteed for every 2 degree of freedom. 2 degree of freedom, there has to be a Hamiltonian, one more constant of motion. Okay, then what Arnold and Liu will assure us is that there will exist a canonical transformation such that you have this I1 and I2 and the corresponding angles theta 1 and theta 2. Yeah. What was the question?
Like I don't know how the torus came.
Because there are these two angles, you see. So any, what did we say? Theta 1 dot is some omega 1 t plus theta 1 0. And similarly, you have theta 2 dot, right? So you have these theta 1 and theta 2 as a function of time. So given that, you see these actions are constants on any given this thing. So the only things that are actually determining this Q and P are theta 1 and theta 2. Given an initial condition, at any time, these actions are fixed. I1 and I2. Let's just fix n as 2. Okay? I1 and I2 are some fixed numbers. In fact, they would parameterize things like the radius of these inner and outer radius of this torus. Okay? You can just imagine, if you wish, just a circle in 1 degree of freedom, like a harmonic oscillator, just a circle. The circle, the radius is fixed. What is moving around is just this theta, okay, which is the circular coordinate. Now you have two of them, and therefore you have this torus. So the torus is coming because the natural coordinate space is that of S1 into S1.
Okay, sir.
Yeah. Just think about it. It's a nice thing. And you also should think of higher dimensional torus, how it looks, how to construct a torus, and so on. Okay, so we have already seen some super integrable thing. All 1 degree of freedom systems, such as simple pendulum, are integrable. Central force problems in any dimension, I have just talked about 2, but any dimension is a very integrable, is an interesting system that's also integrable, and there is an interesting article on this, in fact, by Professor Suresh Balakrishnan, Professor Balakrishnan, and Professor Lakshmi Bala in Resonance. Suresh, you probably have linked that article in Moodle, is it?
Yeah, I have.
Yeah.
The Kepler problem in any dimension is super.
Kepler problem, in fact, that's not just a central force, that is Kepler problem, so that has additional symmetries in any dimension, okay? But a central force in any dimension is also integrable. So uncoupled nonlinear oscillators, of course, because they are uncoupled, okay? So there's just uncoupled, even nonlinear oscillators, it doesn't matter, because each of the individual nonlinear oscillators will be integrable, uncoupled, and therefore it's also still integrable. That even coupled harmonic oscillators are, but now it has to be harmonic. Okay? Coupled harmonic oscillators are examples of integrable systems. And then there are other very things you might not have heard of, but are very famous integrable models in which the integrability need not be obvious. So these are like nonlinear but still coupled. It's nonlinear but coupled things like the so-called Calogero-Sutherland model and so on. There are many, many famous models of integrable systems. But in general, there will exist only smaller than n independent constants. Okay, so we cannot expect. In fact, generally there will be only smaller than the number of degrees of freedom independent constants, and therefore these systems are said to be non-integrable systems. So here are some examples. You take a pendulum, you attach another pendulum to it. It's now 2 degrees of freedom because you have two angles, So you have 2 degrees of freedom, but in general only energy is a constant. Therefore, double pendulum is an example of a non-integrable system. You might have already done Lagrangian of double pendulum and all that standard problem. It's an example of a non-integrable system. If you take a 2-body gravitational problem, that's the famous Kepler problem. But if you take another gravitational problem, gravitating body in the midst of these two, that's 3-body gravitational problem, is a famous non-integrable problem. Of course, the solar system itself has so many gravitating objects in it, and therefore is a non-integrable system. The Sun, Earth, Moon system is a 3-body gravitational problem, very famous non-integrable system. In fact, almost all Hamiltonian systems greater than 1 degree of freedom is not integrable. So I challenge you to take a pen and paper, write down some Hamiltonian or out of your head, non-trivial Hamiltonian, by non-trivial I mean that it should be coupled, Hamiltonian out of your head, and then show that it is integrable. Okay. Typically it will be non-integrable. There is some mathematical statement to that effect. Helium atom, is it a 2-body problem or a 3-body problem? No, I'm talking about atoms, but you can just think about a nucleus and electrons. Is it a 3-body problem or a 2-body problem?
3-body.
3, right? There are 2 electrons. There is a nucleus. So it's actually like this 3-body gravitational problem. Whereas a hydrogen atom is more simpler. So just thinking in terms of classical mechanics, not even quantum mechanics, all non-hydrogenic atoms will be non-integrable. So that's quite a vast amount of systems. And in fact, even hydrogenic atoms, you can introduce like electric and magnetic fields, they will become non-integrable. Almost all force systems, you just add some forcing. For example, a one-dimensional nonlinear oscillator such as a forced pendulum, they will become non-integrable. So almost all systems in nature are non-integrable. Integrable systems are very interesting, but they are of measure 0. Okay, so
regarding point 2, like what about one-dimensional problems?
1 degree of freedom problems, they're all integrable. Because there is energy is a constant, and that's all you need to have.
Okay.
Sir?
You need to have only as many constants of motion as number of degrees of freedom. If there's only 1 degree of freedom, you need to have only 1. Therefore, a Hamiltonian is sufficient. But suppose a Hamiltonian is dependent on time, we'll come to an example like that, then it can be non-integrable. Even 1 degree of freedom can be non-integrable if there are external forces.
Like friction.
Sorry?
Like friction.
Friction is a slightly different thing. I'm restricting myself to Hamiltonian dynamics. Friction, I'm not talking about friction, but there can be forcing. Like you have attached a motor to a pendulum. Or you're kicking it periodically. You have a football, you're kicking it. Your energy is being input into the system. So that sort of thing. So then 1 degree of freedom systems can be non-integrable. Any other question?
Sir?
Yeah.
Could you define again what we define by integrability? Sorry,
Good. Yeah, thank you. So this is what a Hamiltonian system is said to be integrable if there are n independent constants of motion, and remember n is the number of degrees of freedom, and these constants of motion are in this particular mutual involution, that is their Poisson bracket is 0. But I will just encourage you to think about it informally as n independent constants of motion. Okay, this is really a formal requirement, but I will encourage you to think about integrable systems as just n independent constants of motion. So that means that there are sufficient number of constants of motion.
So this is slightly different from like our usual integrability, right? Because even like double pendulum and all, if we can do numerical integration and solve numerically, like
that every system is that way integrable. Okay, every system, after all, you can numerically integrate. You see, that is a different notion. of, I wouldn't call it, well, it's not called an integrability thing as far as I know, but those things, I mean, I'm assuming that your forces and so on are such that, there is some smoothness conditions so that your differential equation has uniqueness solutions. Okay? That we are assuming. Mathematician would probably state that up front. Okay? But that way of integrating numerically any of this thing, any system is that way solvable. Okay? But it's a good point. Is that clear? Any further clarification?
Sir, can we say in a two-dimensional system, even if we have a single symmetry, it will become integrable?
Okay, so talk a little bit more precisely. Okay, when you say two-dimensional, 2 degrees of freedom, 2 degrees of
yes,
freedom
sir,
system. Okay, so what is the question? 2 degrees of freedom. If you have,
if we have some symmetry, then we will get a constant of motion corresponding to that. And we have
symmetry is very important. I mean, not any symmetry.
Continuous symmetry. A continuous symmetry.
Okay. Yeah. And if you have a continuous symmetry, then yes, because associated with a continuous symmetry, you will have a constant of motion. And that continuous symmetry must not be, I mean, even time translation is a continuous symmetry. That leads only to the conservation of the energy, which we are assuming is already there, or the Hamiltonian is constant. Apart from that, there should be one more constant. So in a 2 degree of freedom system, if there is any one constant of motion in addition to the energy, which is not just a function of energy, then it will be an integrable system. Like for example, in this central force problem, angular momentum. Okay?
Okay, sir.
Yeah. So this is just stating that, let me not go through this. Here is a double pendulum. Now, I said about integrability, non-integrability. You can ask in some sense, who cares? That is to say, is there any qualitative difference between an integrable and a non-integrable system? So now I want to tell you that there is a very important difference between integrable and non-integrable system. A non-integrable system can lead to orbits which are known to be chaotic, which can look very random. So here is an example of that. Famous example is a double pendulum. I don't know how many of you have seen a double pendulum. Those of you, I would invite you to my room if you have not seen it, but you may be far away from me metrically at this point. But it's very easy for you to also make a double pendulum. Okay, make it and then swing it. So you will see very complicated motions if the energy is large. For small oscillations, it will look like 2 coupled harmonic oscillators. You will have normal modes and so on. This is a standard exercise. But if the energy is large, you will get into orbits which are very irregular. So what I have shown here is some trace of the second particle. So trace of the second particle, it doesn't follow some simple curve. It's going all over the place and it can appear to be chaotic. Here is an example of a 3-body problem. So 2 massive objects and a third light object which is moving in its moving between these 2. So it's flipping between this and that. So this object, this is the trajectory of this in real space. So it looks very chaotic and irregular. And in fact, non-integrable systems in general have orbits which are not stable. They are unstable. So in fact, they are not just unstable, they are exponentially unstable, and they are said to be sensitive dependence on initial conditions. So that means that if you have 2 trajectories which have very initial conditions are separated by a small amount in phase space, then after some time t, they are separated by a very large amount which is exponentially growing in time, and that exponential rate is called the Lyapunov exponent. Okay? So in general, sensitive dependence like this, exponential divergence of trajectories, plus the fact that they cannot go arbitrarily far away because the phase space is compact. Let's say total energy is constant. You have that kind of a 3-dimensional compact space, leads to chaos or deterministic randomness. You see, this doesn't look very chaotic. They can just go away from each other. But If suppose you are in a surface which is bounding these two, they are bound to come back. Okay, they cannot be exponentially separating like this, but they are bound to come back, but they are locally always exponentially expanding, and therefore they are unstable, and therefore this leads to this behavior of chaos or deterministic randomness. We offer elective courses in dynamical systems. If you want to study this more deeper, you will have to take courses in that. In fact, all forced systems, or those with more than 1 degree of freedom systems, are chaotic for some initial conditions, not for any initial conditions, but for generic initial conditions or for sufficiently large energy, they would become chaotic. Here I give you an example of 3 pendulums. Okay, I found this thing. I forgot exactly where, but there are now 40 triple pendulums. Okay, this is a triple pendulum. 1, 2, 3 degrees of freedom. Okay, there are 40 of them, meaning that there are 40 different initial conditions. You don't see, you see only one of them. Okay, now we are going to start the dynamics and see what happens to these 40. So you still see only 3. With time is going on. Now you see each one of these 40 has now separated. Each one is quite independent of the other. If you look at it as if they were, suddenly you see a rainbow, all of that is these 40 different things with each different colors, and they are completely different from each other. And the time till which that they appear together is this thing which is, it's determined by the Lyapunov exponent which I wrote. So this epsilon is how close these things are. So if they are very close, then it will take longer, but doesn't matter. Essentially, this rate is given by the inverse Lyapunov exponent. So the larger the Lyapunov exponent is, the faster they will diverge from each other. So this is you can ask what is the origin of randomness in physical systems if everything is deterministic. So chaos is one of the answers for this. As you know, the planet Pluto has been demoted from planet. It has actually chaotic motion with the Lyapunov exponent of inverse 20 million years. Okay, so, and for weather predictions, typically local weather predictions, the Lyapunov exponent is such that you can only predict for 5 days the weather. So they are all nonlinear systems with this kind of things. So there are 2 degree of freedom systems. As I said, that's sufficient. You have a circular billiard, so this is just a particle moving inside this, bouncing around this. There is now additional conservation of angular momentum because of the symmetry of this, and therefore this is an integrable system. This is just a particle moving inside an enclosure, 2-dimensional enclosure like this. It is hitting this boundary, coming back. Okay, this is that's why they are called billiards. So this is a rectangular billiard or a square billiard, again integrable. It turns out very interestingly that an elliptic billiard is also integrable. It's a challenging exercise. I encourage you to think about it because it doesn't have circular symmetry. So apart from energy, what is the other constant of motion you have to think about? There is a constant of motion also related to angular momentum, but angular momentum itself is not a constant. So now you can go ahead and break the symmetry any way you want. So here I have broken the symmetry by taking a circle in the middle of a square. So there is no circular symmetry anymore, but also this separability, which is the responsibility for this being integrable, also is gone. And this is called a Sinai billiard, fully chaotic. So this is how the trajectories look. This is another billiard named after another Russian guy called Dunimovich, or also called the stadium billiard, which is just 2 semicircles, straight lines in between, fully chaotic. This is a cardioid billiard, also a simple curve, 1 plus epsilon cos theta, and for epsilon equals 1, this will become fully chaotic. So this is called a cardioid billiard. So you see very simple systems. It's just a free particle in this enclosure can have very complicated dynamics. Okay, so let me not probably go into that, and because I think I should end in a few minutes. So this is an example of 2 degrees of freedom system. Harmonic oscillator. This is just harmonic oscillator. This will be integrable. But you add in interaction between the 2 harmonic oscillators, cubic interaction potentials now. So this is the smallest away from this quadratic. This is known as a famous thing. It was studied in the 60s by these astronomers as some effective galactic potential. Okay, and they studied it numerically because at that time computers were available, and as somebody said, you can put anything on a computer and integrate it. And they found very interesting trajectories, what we call them chaotic today. Here is another example. Chaotic is a coupled quartic oscillators. Okay, so I'm showing you. So these are standard examples. Here I'm showing you this quartic oscillator example. The phase space is 4-dimensional. We cannot deal with a 4-dimensional phase space that easily, but there is a thing called a section, a Poincare surface of section, which will tell you a cut through the thing, and that it tells you something about what's happening in the entire phase space. And here you can see some Poincare surface of section, so you can just imagine that these are some sections of orbits, and this looks like a regular non-chaotic things or integrable systems. As you increase some parameter, in this case the coupling alpha, this nonlinearity parameter, or this parameter alpha is being increased for a fixed gamma of 1, you can see a transition to chaos. And you can see that here, this kind of thing here is a single trajectory going all over the place. Okay? So in fact, non-integrable systems are the foundations of why statistical mechanics should work. Things like ergodicity and so on. Here another simple example of a pendulum, but now it is time periodically kicked in time. Okay, as Suresh said, I work on simple models like these. So this is, you can now derive a map for this, a map meaning that it's kicked in time. So you can ask, what is Q and P related after time kick n plus 1 to the position momentum after kick n? Okay, well within your scope, you can derive this thing. So now you don't have to solve a differential equation anymore. You have to only iterate this. So it's even simpler. Those who know any MATLAB or Python or any programming can do this trivially. And then you can study what is happening to this. There's only one parameter k. If k is 0, this is 0, then it's clearly just a free particle and it's an integrable model. But if it's not, then it becomes non-integrable. And you will have these kind of orbits. So let me just show you some orbits maybe, and then I will end. This is all for this. This, by the way, is called the standard map. There are many names to it. So this one looks almost like a pendulum phase space. Okay, you can see an unstable fixed point and a stable fixed point, and then these kind of rotational orbits. This is for k is 0.2. And when this kicking is increased, you can see that each of these orbits is now deforming very interestingly. These are called nonlinear resonances. You can see these kind of islands which are forming. And when these nonlinear resonances grow and intersect, they lead to chaos. So you can see that this is 0.8. And then as k is increased even more, you can see that it leads to very these kind of orbits which are roaming all over the place. So there is integrable and non-integrable or chaotic things. So wherever you see the splatter of points, it's chaotic. In fact, here it's just one point iterated all over the place. So this would be having a very erratic looking motion here, random looking motion here, and this would be example of chaotic. But in between there is some initial conditions which if you start will not be chaotic. If you go to very large values of k, here I have shown for 9, it's fully chaotic, you will not find any islands of regularity. But at 9.26, you will find some islands of regularity coming in. So these are very simple systems, but actually there are many open questions even in this, and there's a very active study on mathematics of, dynamical systems and so on. As I said, individual trajectories become unpredictable, but simple statistical behavior emerges. So you have things like ergodicity, phase space, time average are equal. Mixing happens within this kind of phase space. Okay, so these are the essential things for statistical mechanics. So if you want to understand more, you will have to take this elective And may the chaos be with you. Thank you for your attention. That's my presentation for today.
At the value of k, where you start to lose every island, is that the place where we give up on determinism?
We never give up on determinism, okay, in the sense that everything is deterministic. Okay, there is no, let me be clear that there is no randomness in this model, right? I mean, there is no coin toss, or, when you do a problem like a random walk, you toss a coin and say, if it is head, I'll move right, and if it is tail, I'll move left. No such thing here. These are all deterministic models. But your question is there some value of k at which the chaos arises? A sharp value of k. The answer to it is there is a value of k which has been identified, which is close to 1, and it's a very interesting application of renormalization theory, by the way. You might have heard of renormalization or will hear of renormalization theory. Because actually behind these things there are fractal objects. If you look close within this, you will find as if this entire phase space was there and so on and so forth. So using that, people found out at what value of k, these kind of tori, they are called actually Kolmogorov-Arnold, the same Arnold who comes in the integrability condition, Moser tori, when do they break? Because once they break, then you have what is called widespread chaos. So the last of them breaks around k is 0.9. So at that point, one identifies a value of k at which there is widespread chaos. But if you ask me, is there a value of k beyond which it is fully chaotic for every trajectory? The answer is actually no. That means that, I gave you this example here. K is 9, it looks like it's fully chaotic, everything, but k is 9.26, you find islands of regularity. So this is where I said that things get complicated. There are some mathematical theorems which say that, which give you some conditions on k for it to be fully chaotic and so on. But they're not simple enough. But there are other models for which you can have such clear transitions from. But as far as physicists are concerned, these may be very small and they will not affect us. We would say that k greater than 5, for example, would be a kind of transition to full chaos.
Okay, sir. Thank you.
Sir, when you say fully chaotic, is there some kind of way to define fully chaotic, or we just have look at these graphs and using that say some cases are fully chaotic?
Yeah, it's a good question. These graphs, as you're calling them, they are Poincare surveys of sections. They can be hard to find if you go more than, so this is a 2 degrees of freedom, 1 degree of freedom with time. Okay, so we could plot it easily. We had only Q and P. But let's say that you have a 2 degree of freedom thing, let's say a double pendulum which is kicked. You can do it. It will lead to a 4-dimensional map. I wouldn't try to plot anything. Okay, so it will become hard. So, but anyway, what one means in principle when one says it's fully chaotic is that all orbits have a positive Lyapunov exponent. Okay, so for given any orbit, you can calculate a Lyapunov exponent that it is positive. But to prove such things is actually very hard. Even for these kind of billiards, it's very hard to prove that something is fully chaotic or not. Okay, but this has been done for these. For Hamiltonian systems, it's even more difficult to prove that something is fully chaotic. Good.
Sir, are the dots for the chaos actually circles, tiny circles?
No. No.
Okay.
They are just dots. Because that is just plotting Q and P at any given time. So where is the circle coming from? In fact, the circles that you're seeing are themselves not circles. These curves which you're seeing are actually points which are falling in something which you are imagining to be a curve. If you actually do it, and I encourage you to please do it, you will find that this one here will come here and then go there because it's a map. It's not obliged to go like this. Don't think that that's happening. It's not like like your phase space of a harmonic oscillator where things are going like this. This is not an orbit. This is a collection of points which is giving you an illusion of an orbit.
Okay.
Yeah. So I mean, I didn't have time to go into the details of this, but as you see, it's a very simple map. You can Google standard map. Okay, standard. It's called standard because a lot of Hamiltonian systems are locally like these. By the way, the study of quantum mechanics of such systems has been done for many years now. It's it's come back in style now, and there's a lot of experiments. So there are cold atom experiments in which they kick atoms and with lasers, and they simulate such things, and there are very interesting differences between classical and quantum chaos. Are there any questions for relevant to this class?
Sir, could you show the slide where you where the uncertainty was like exponentially magnified with time? There's some map.
It was just a sort of a schematic, yeah.
So, like, does this in some way imply that like if the uncertainties arising from like Heisenberg uncertainty principle, could that have a like effect in like macroscopic systems, chaotic systems?
Yeah, it's a good question, but it gets somewhat complicated because once you say Heisenberg and so on, you're thinking of quantum mechanics, and when you think quantum mechanics, the phase space is gone because you see position and momentum cannot be measured together. So the notion of phase space kind of dissolves. Okay, and in fact, what happens is that since there is no point, as you said, there is no one point is not well defined, but maybe an Heisenberg uncertainty circle is defined, like a coherent state is defined. Then quantum mechanics, in fact, softens chaos a bit because it doesn't allow for uncertainties which are very small. So in a way, it takes the edge of classical chaos. So I think the main message is that you have integrable systems which have more than or equal to the number of degrees of freedom constants of motion which are independent, and you have those which are smaller, which are typical non-integrable systems, and these non-integrable systems can host a variety of very interesting trajectories which are typically chaotic. But in a generic sense, it will be like this kind of mixed phase space. By the way, this is a map like what I showed, but for a billiard with this shape, 1 plus 0.3 cos theta. What is plotted is where it is hitting this one here, and the angular momentum or this cos theta kind of thing when it's hitting this. So whenever it hits the boundary, you record where it hits and in what direction it hits, and you will get this map. Next time it goes. So these orbits here, which are regular orbits, you can see this periodic orbit here, that is actually corresponding to this. This corresponds to a straight line orbit like this, okay? And this one in the blue corresponds to some orbit like this. But around that, you will find some interesting orbits. So actually, even this simple picture and even this simple thing has a whole host of very interesting orbits, and this is called a mixed system because it has both chaos and regular orbits, depending on the initial condition. Okay. Suresh, should we close if you're there?